Okay, so it gives me the 1.95 in the same graph that you saw over there. Okay, so to summarize, what I'm trying to say is, turn the light on. Okay, so as we go through a neural network, right? The difference, as you will see, is the model over here will be our weights instead of A and B, like you saw in the previous example. Okay, and the biases. If you have a single neuron, there might be 1 or 2 weights over here, or depending upon how many inputs we have, and 1 bias. If we have 100 neurons, 100 weights connecting to each input, so depending on the number of inputs, this will be a weight matrix, and each neuron will have its own bias. Anyway, but the important point to note is what we'll do is exactly the same thing I showed you through the linear least squares optimization, meaning we'll create a cost function. Okay, let's pick a very simple neuron example. Okay, let's say I have some activation function. So 2 more minutes, then I'll stop. Okay, for today. Okay, so let's say here's x1, w1, x2, w2, 1b, right? So if I take a look at the sum and pretend the activation function for right now is just simply bypassing, connecting to the output. So if I write the equation for S, what will this come out to be? S equal to w1 x1 plus w2 x2 plus b, right? Then what will be the actual output? Same as S, meaning same as, because right now no activation function, w1 x1 plus w2 x2 plus b, right? Now let's set up the cost function or the loss function. So if our loss function is a minus or y minus, doesn't matter, y minus a squared, y is the expected output, a is the actual output. Okay, so what would it look like? See, this is my actual output, right? And just so that remember this 2 will, as I take the partial derivative, will come over here so that I don't have to keep worrying about multiplying by 0.5. Let me make the loss function in the beginning half over here. As long as I'm minimizing this same thing, it doesn't matter what constant I multiply it with. So anyway, this could be written as y minus w1 x1 minus w2 x2 minus b squared. Everybody agrees? Okay, so if we were to find, we feed in an input, right? It will give us some actual output. We already know from the training data what the expected output is, which we are calling y. Okay, so another goal is to go back and figure out what should be the w1, w2, b. So again, we can use the same optimization, mathematical optimization criteria, meaning take the partial with respect to w1, with respect to w2, with respect to b. So we call them gradient. So partial L over partial w1, because our model parameters are now w1, w2, and b, right? So if you did partial L over partial w1, remember 2.5 will cancel. So then what will this become? Y minus w1 x1 minus w2 x2 minus b, and then what? And then with respect to w1, just the x1, right? Or negative x1? Negative x1, so I put the negative over here. Okay, or I could write it now simply y minus, because really this is my actual output if you think about it. So I could leave it as y minus a times x1, negative. And so as you will see when we write the code, we refer to this partial derivative as the gradient. So the gradient of W1, so I'll just call the variable grade of W1, grade, but basically means it will be this, right? Okay, now can we find the gradient with respect to W2? What will that be? So grade W2 minus y minus a x2, everybody agrees? Okay, what will be the gradient with respect to the bias? And the derivative of the inside with respect to b is 1, right? Yeah, I put the minus over there. Okay, so these are the three equations. Okay, unlike before, where we were simply setting it equal to 0, summing it over all the data points, and then determining the value of the parameters, okay, by solving the three equations. Now what will the difference is, because we have a lot of training data. Okay, so typical process is forward the data, the training data, compute the A. Based on the y, compute the gradients. Once the gradients have been computed, then each weight over here, remember in the beginning this is randomly initialized. Okay, so now we will say W1 equal to W1 minus some kind of a learning rate multiplied by gradient of W1. So this is how we will adjust W1 after every training task. What exactly is a learning rate? It's typically a value like 0.01. Based on some experimentation, you will adjust it. Then later on, I'll show you some dynamic learning rate techniques, some algorithms that we will go over, which performs a better optimization, right? Same way you get the idea, W2 will be updated, W2 minus the learning rate times grad W2. And the bias will be updated as bias minus the learning rate times the gradient of the bias. So this is essentially our backpropagation algorithm for a single neuron. Okay, for multiple neurons, it becomes a little more involved. In the next lecture, I'll go over what that algorithm is when multiple neurons are involved. But for a single neuron, as you can see, nothing complicated. Based on the concept of the linear least squares, all we are doing is computing the gradients. Based on the gradients, whatever randomly initialized weights and biases we had, we are updating those. Okay, one more minute, let me demo the programming that does this for you. So that at least first week's topics are covered nicely. Okay, is everybody done writing? Or, okay. So just 2 more minutes, let me show you the code. Programming of the exact same thing that I showed you, so that you can see it. If we apply this backpropagation, it learns it properly. And then I'll be giving you an assignment, which I'll put it on the website. Every week you have to do 1 or 2 assignments, okay? Because this is how we learn. Nobody can just read and learn deep learning, okay? You have to get involved, program, and don't worry in the first few weeks, if by the deadline you haven't done the program, I'll give you more time so that gradually you develop your programming expertise. But we'll be doing some lot of challenging, lot of nice work. So do not relax. Okay, so whatever I'm showing you, I'll put it on the website. For the course? I forgot to give. Okay, sure. I'll mention that in 1 second. Just 1 second, let me launch it again. For some reason it wasn't opening. Okay, so the project, once you locate it on the website, will be called, before I forget, the course website, as I mentioned, is http kiwi.bridgeport.edu/CPEG586. Okay, the username is ubstudent. Password is ubstudent 2018. Okay, and once you go to the website, okay, let me show you. CPEG586. Okay, so right now it only shows up the lectures for the last year. So I leave the last year's material on the website in case all the assignments that you see were given last year. Obviously, I'll say 50% of these will change because new things have come up since last year. And we'll try to improve the course also compared to the last year. So I'll add one more link over here for 2019. Okay. Anyway, so once you see this is where ubstudent 2018 you will enter. Okay. Anyway, back to. So suppose what we wanted to do is we wanted to make a single neuron network. Okay, X1, sorry. X1, X2, W1, W2, and one bias. Okay, nothing over here, and Y. Okay, so I wanted it not for classification, but for regression, so that we feed in X and Y. So this corresponds to it, the X and Y. Okay, so I wanted to make our network learn. For example, Y equal to, what was it, 2X. Okay. Let me just check what equation I made it learn. 0.3x plus 2. Okay, so I want to make this network learn 0.3x plus 2. Okay, so I'll give it a lot of examples. Like, for example, if I give it an x of 1 as a training, right? x1 of 1. Remember, x1 corresponds to x, x2 corresponds to the y coordinate. So if I feed in 1, what should be, if it's a point on the line, it should be, so x2 will be 2.3. Everybody agrees? What if I feed in x1 of 3? Then this will be 2.9. So remember, in this example, I'm not having it learn the below the line or up above the line. I'm having it learn the equation of the line, which is called regression, right? Okay, so that after it's learned, if I feed in, for example, x1 of, let's say, 6, then what output will it produce? 3.8 automatically. So that's the goal, right? So we went through, set up the error function just like I showed you on the board a minute ago. All we have to do is just put 2 loops over here. One for the training loop, which we call the epoch. And then one for the number of epochs. One more loop. Start the weights biases initially, give it some training data, and have it learn. Once it's learned, okay, suppose this is what we were making it learn. Can you guys guess what will be the value of W1 and W2 and the B would have learned? Sorry, in this case, okay, in this case, do I need that? Okay, let me show you the code. Okay, my mistake. For regression training, yeah, we only need one weight, sorry, not 2. For regression, all we need is W1, X1, and the bias. For regression. For classification, we need both. Okay. So after it is learned, remember we were making and learn the equation 0.3x plus 2. What will it find W1 to be, B to be? 0.3 and 2, exactly. So if you take a look at the code over here, and again I'll put it on the website, it's a double nested loop. Can you guess why it's going through 10 times? Because I have 10 training examples. What are the training examples? Here's the expected. For example, for x of, let's say, 2. If x3 is 2, remember we are making it learn 0.3x plus 2. So what will be the expected in this case? 2.6, exactly. So if I go to y of 3, it will be 2.6. Anyway, so I created some 10 training examples. So the inner loop basically goes 10 times. This is one epoch. And then further, I run it 1,000 epochs. Okay. Each time we compute the gradient, just like we discussed. So if you take the partial derivative with respect to W, you'll see what's coming out multiplied by X, right? And the bias was 1. And then 0.01 is the learning rate. So each time I update the weight, I update the bias. Once it's done through the 2 loops, I print out W1 and the bias. So if I run it, okay, so take a look over here. If you can't read it, W1 is 0.30000. B is 1.9999. So has it learned regression there? Right? Okay, so same way, I also have another example for classification, where is it below the line or above the line? So those are the two buttons. I'll put some explanation on the website so that as you go through it. So give it a try. I'll give you step-by-step examples, meaning how should you look. As long as you have the Visual Studio, you can, if you don't have the Visual Studio, you can download Visual Studio Community Edition. This is free. Okay, and make sure you put a check mark on the, I forgot it's called desktop development or whatever. Okay, then once you have the Visual Studio, I'll give you the screenshot, what do you have to click, how to create the project and so on, and how to try this code. So, so your first assignment, like I said, you will do a nonlinear least squares regression, least squares optimization using the partial derivatives. I'll give you some data. You'll give me the model as you compute. And then I'll give you maybe a three-dimensional problem over here so you'll convert the 2D to 3D and see if it is working correctly or not. Okay? I'll stop here. Thank you for staying up a little bit late, but it's important for us to keep making progress. If you have any questions, let me know.